Today's topic is going to be on Riemann sums. Now, previous video, what we went over was doing the approximation of an area underneath a curve, and what we came up with was that essentially that if you had some curve between 2 points, that you could break these up into a bunch of little rectangles and calculate the area of those rectangles and then add them all up, and then you'd get an approximation of the area that's underneath that curve. Well, in this case, Riemann sums is basically the exact same thing, except typically you take them at the endpoint. So you take an approximation of a bunch of, right there at the endpoints. So when you start at 0 or whatever that would be there, and when each rectangle starts, that's where you take your limit at starting. But in this case, it's basically the exact same thing we just did. It's representing it as a sum, and I'm going to skip that step because that's just very basic and it doesn't really need any sort of tutorial. So, based upon breaking the area under the curve into tiny rectangles, so infinitely small, with Riemann sums, we're evaluating the sum of the area at a set amount of rectangles. So how this will change the answer is very simple. Is that, and we've been over this before, is if you imagine that you have a curve and you have just, let's say 4, we'll make it simple. You have 4 rectangles that are going to add up the area of this whole thing. Well, you can see that there's going to be areas here that are going to be outside of that curve. So therefore the approximation is going to be a mere estimate, and it's just going to be off. So the more rectangles that you have, the smaller and smaller those are going to become. So if you have infinitely smaller amount of rectangles, even infinitely small space between them all, that's going to just add up to give you the entire area. Then that's going to be underneath here, and that's pretty much an exact approximation, or about as close as you can possibly get. So what we're going to go over as well is the midpoint rule. And this is very, very similar to the Riemann sums. It's basically an application of Riemann sums, and instead of taking sum of rectangles for a set for every starting and end point, what we're going to do is that you're essentially taking an average of the location of where that's happening in your lower axis here, and you use that to give you the middle point, and then you take the height there at that midpoint. It's pretty straightforward. So, in better terms, so if you have a function f of x where the x values are going to be the midpoints of the given rectangle that we're using at that point in time, and that point x is going to be denoted x bar. So that means that the midpoint function will be denoted fx bar. And that simply just means the midpoint. So thinking back to the video on definite integrals, the limit was represented as a definite integral. Similarly, in this case, we're going to represent a definite integral as a sum of the areas of all these triangles. So if we have a definite integral, some f of x dx, and we know this is going to be a sum of the rectangles of n amount of rectangles, some ith integer starting at 1, and it's simply just going to be adding up the area of all of these midpoint functions. So that right there, as we've done before, that's because it's the area, that's the height. We know that. Looking back on here, that's just going to tell you how high it is. And then multiply it by, same thing, your delta x, which is the width. Same as before. And that's simply just going to be denoted as you start at fx bar 1, and you're going to go all the way to fx bar n multiplied by delta x. Same as before, delta x is going to equal b minus a over n. and our xi bar in this case. Now, simply just going to be the average between the endpoints. So what you're going to have is xi plus xi minus 1, all divided by 2. So, let's go over an example. And if we have a definite integral, it's from 0 to 8 of sine of the square root of x dx, and it's going to equal 4. That means our delta x right away is going to equal 8 minus 0 over 4. It's going to equal 8 over 4. It's going to equal 2. We're going to have 4 midpoints. We know that because we have n equals 4. And we know that our endpoints, since we have 4 rectangles, is going to go from 0, 2, 4, 6, and 8. So that means that the middle of each one of these rectangles are going to be located at x equals to 1, 3, 5, and 7. So going back to our formula, what this allows us to do is, remember what we had, the sum. Now we're going to have 4 for n, starting at 1, and we're simply just going to have to add up those sums. Okay, so what that does is that you have sine of the square root of 1 plus sine of the square root of 3 plus sine of the square root of 5 plus sine square root 7. These are all going to be multiplied by 2, because remember that's your delta x, and that's going to give us 6.18. It's a 2. Alright. And that's just how you do a simple midpoint rule, the application of Riemann sums.